So the first will be about chapter 5, as we said. So the chapter 5 course revision questions. The first thing is talking about the molar volume of the gases. We know that the molar volume of the gas is meaning the volume of 1 mole of gas. The volume of 1 mole of gas. We already know from the law of Avogadro's law of gases that if two gases have equal number of moles, they will be having equal volumes. That's why we made a rule and we said that for any gas which is at RTP conditions, the volume of 1 mole of this gas will be equal to 24 decimeter cube. And if you get 1 mole of any gas at STP conditions, you will find that its volume is 22.4 decimeter cube. So what is the RTP? Because he will ask me in the exam, I will tell him the RTP is that specific conditions where the room temperature and pressure, the temperature is going to be 25 or 20, 20 or 25? 20, right?
RTP?
Yes. So what about STP?
Machine 22.4.
The 22.4 is the volume, but what is the temperature? At which temperature and at which atmospheric pressure?
Yeah, 1 atmospheric pressure.
1 atmosphere unit per atom is 1 atmosphere. And what about the temperature? 0 degrees centigrade and 20 degrees centigrade. If you have any gas, so if it is hydrogen, helium, nitrogen, whatever gas, you measure 1 mole of it, 1 mole of it, 1 mole of it, they will all have the same volume at RTP. What will be the volume at RTP? 24 decimeter cube. If you measure their volume instead of RTP at STP, it will be 22.4 decimeter cube. Okay, this is called the molar volume of the gas. Instead, here I have 1.1 mole of oxygen gas and 0.4 mole of nitrogen gas are placed in a container. The total pressure in the container, find the volume of the oxygen gas. We know that this is a tricky question, that the volume of gas is the volume of the container. So volume of gas equal to volume of container. So it's equal to 20 liters, and I will not do anything with the rest of the question. Then the kinetic theory of gases will ask me how to measure the temperature using, or how to measure the pressure using a manometer, either an open-end manometer or a closed-end manometer. And we can measure also the atmospheric pressure using a different device, which is called the barometer. So what is the use of barometer? It's used to measure the atmospheric pressure. What is the use of the manometers? The manometers are used to measure the pressure of gas, and there are 2 types. The first type is the open-end manometer, open-end, and the other one is the closed-end manometer. The open-end manometer, if you look at it, it will look like that. So at the end, it's open, it's like that. And there is the gas. The gas inside has a certain pressure, and outside the pressure that I have is the atmospheric pressure, because it's open. So if the pressure of the gas is equal to the atmospheric pressure, the 2 lines will be at the same line. Why? Because this is pushing from here the same way this is pushing from here. So this means that the atmospheric pressure is equal to the gas pressure. Both of them are equal. So what is the atmospheric pressure? The atmospheric pressure has to be mentioned every time in the atmospheric pressure has to be mentioned. Pressure of the atmosphere has to be mentioned. Why it has to be mentioned? Because it differs, right? If you are at sea level, the atmospheric pressure differs from if you are on a mountain, if you are on the Himalayas. As you go up, what happens to the atmospheric pressure? As you go up, the atmospheric pressure decreases. Because if you are a man and standing here, the column of air on your head is like that only. But if you are a man and standing here, the column of air on your head is from here until here. So this means that this is all the atmospheric pressure on your head. So the atmospheric pressure increase as you go down. But if you go up, like in the Himalayas or any place, the atmospheric pressure will decrease. The atmospheric pressure will decrease as you go up. Go up means in a mountain, in the Himalayas, whatever. Okay, so he said atmospheric pressure, he has to measure it. He has to mention it. It's equal to 750. It's equal to 660. Did you see there is different numbers? That's why he must tell us. The only thing that we need to know in addition is how to change between the units of the pressure, because the pressure in our syllabus has 2 units. Outside the syllabus, it has more units, but in our syllabus, 2 units only. The atmosphere, which is called ATM, and the other one is the millimeter Hg. We know that 1 atmosphere is equal to 760 millimeter Hg. If he give you any number in atmosphere and asked you to change it into millimeter Hg, you can only do the cross multiplication. So if he told you I have 0.5 atmosphere, what will be the pressure in millimeter Hg? I'll cross multiply, so 760 multiplied by 0.50. If he give you the opposite, then it will be still the same thing. Also use the cross multiplication. If he told you, I have 380 millimeter Hg, what is the pressure in the atmospheric? Just also 380 over 760, I think it's 0.5. So this is how to convert between the units. But the value itself has to be given because you cannot assume it, We said that if the pressure line is the same as the distance of the gas line, so if the pressure line is the same as the line of the gas, then in this case you will say that the pressure of the gas is equal to atmospheric pressure. So if the atmospheric pressure is 700, the pressure of the gas of the pressure will be 700. Why? Because they are all at the same height. But what happens if the atmospheric pressure is pushing more, which means that it is higher? Like if the atmospheric pressure is 700 and the pressure of the gas is equal to 600. Since the gas of the pressure is only 600, for example, so it cannot push too much. It will be pushing less. The pressure of the gas, and this line will be lower, and this one will be higher. Why this one is higher? Because this one pushed more. Why this one pushed more? Because this one has a higher pressure. So in a summary, Mr., if you want to find out the pressure of the gas here, all you have to do is subtract, right? You will say the difference. So the difference is 100. So subtract the pressure of the atmosphere minus the distance. You will get the pressure of the gas. So in our example, 700 minus 10 minus 100 is equal to 600 millimeter Hg. What this means that what is more than what? The pressure of the atmosphere is more than the pressure of the gas. What if the opposite happens? The pressure of the gas is more than the pressure of the atmosphere. In this case, the gas will be able to push more than the atmosphere. So the line of the gas will be lower and the line of the atmosphere will be higher. Why? Because this one is stronger, so it pushed more, while this one is weaker, so it pushed less. If the distance is 50, so this means that the pressure of the gas is more than the pressure of the atmosphere. Let's say in our example, it was 660. It is more than it by 50. So in this case, the pressure of the gas is equal to the pressure of the atmosphere plus the distance. In this case, the plus. Or, Mr., you can stop all this blah, blah, and then tell me the summary. The summary, if the pressure of the atmosphere is higher, so you will subtract. If the pressure of the atmosphere is lower and the line is higher, so just add this number. So it's equal to 660 plus 50, so equal to 710 millimeter Hg. And because we know that the boiling point is the point at which the atmospheric pressure is equal to the vapor pressure, so Mr., you have already told me that this one is equal to Boiling point is when the atmospheric pressure is equal to the vapor pressure. And you already told me that the atmospheric pressure here has decreased. The decrease. So what happens? What should happen to the vapor pressure to adjust? The vapor pressure is still the same. So if this one decreases, the boiling point has to do what? Has to, what do you say? Increase, right?
Oh,
And then the opposite, Mr. If the boiling point is when the pressure of the atmosphere is equal to the pressure, vapor pressure. Mr. If the boiling point, what will happen to it if the pressure of the atmosphere has increased like that? For this one to increase and this one to be stable, this one must decrease. So the boiling point will decrease. So as you go down, like to the under the sea level, the boiling point will less. So these people living in Holland, they can drink the tea very fast. Why? It's not that much, by the way, because for us, it will be 100 degrees centigrade. For them, it might be like 90 or 95. The water might boil. So if they have a kettle, and they are heating water, the water will boil at 95 degrees. But if you take the same kettle and try to go up, then the water might boil at 103 or 105. The boiling point of water has changed, Mr. Yes, this is what we are talking about. The boiling point here increases and here decreases. The next kind of the questions, if you have a closed-end manometer, if you have a closed-end manometer, it will be a little bit different. What is going to be different, Mr.? You are going to see that you are not at all considering the atmospheric pressure because this is closed-end. So it's not related by any means to the atmospheric pressure. To the atmospheric pressure, not related because the atmosphere does not go inside because it is closed in the manometer. So if it is closed in the manometer, what is the pressure of the gas, Mr.? There are three cases. The first case is that if I have a defect in my manometer, like it has a hole inside. If it has a hole, what will go inside? The atmosphere. So the atmosphere will go inside. If there is no air going inside and it is working, then here should be vacuum. What is the meaning of vacuum? There is no air. Then what is there inside? Nothing. There is nothing inside. Practically, vacuum means zero particles of anything, no air, no oxygen, no nitrogen, nothing at all. So if there is vacuum, then the pressure is equal to zero because the pressure of the gas is coming from the particles hitting the walls of the container. So if there are no particles inside to hit the walls of the container, so there is no pressure. So the pressure is equal to zero, and the pressure of this one has three cases. The first case, if the pressure of this one is higher than this line. The pressure of this one is higher than this one. What does it mean? It means that I have, oh, sorry, I don't need to remove this one. I'll just remove this one and make it like that down. So this means that the pressure of this gas is more than zero because here is vacuum and pressure of vacuum is zero. So the pressure of the gas is more than zero, more than zero. More than zero by what? By this distance. So all you have to do is add by the distance. So if the distance is equal to 10, so the pressure of the gas is equal to 0 plus 10. So that's only 10 millimeter Hg, for example. But what if the distance, Mr., is less or it is equal? Mr., if it is less or equal, then the two cases tell me that there is something wrong because this is vacuum. It should be zero. Do you want to tell me that the pressure of the gas is less than zero? It does not make sense. So if it is equal or it is less or it is more means the pressure is less. So it's less than zero, which does not make sense. Then there is a defect. There is a defect in my device. So like what? Like there is air coming inside, like there is a hole. Because if there is air or hole means that the pressure now is not of vacuum. It's now the atmospheric pressure. So it makes sense that it might be weaker or stronger than the pressure of the gas, but you cannot say that the pressure of the gas is less than zero. The next type of questions is repeated in these questions answers. So for example, the diagrams of the open-end manometer can be easily found from here. If the difference between the heights is 150 and the atmospheric pressure is 800, This means the atmospheric pressure is higher than the pressure of the gas, higher than it by what? By the difference, and the difference is 150. So we need to add the 150 to the 800 or subtract it from the 800. What do you need to do? You need, Mr., to add or subtract.
We need to add.
Yes, you need to add. Very good. Because if you add it, it means that you have increased the pressure more than the atmospheric pressure. Because it means that the pressure of the atmosphere is weaker. The pressure of the atmosphere is weaker. That's why it pushed less. And here is one. Or, Mr., you have just told me a few minutes ago that if it is the pressure of the atmosphere is less, so you will add. If it is more, then you will subtract. This means you will subtract 700 minus 120, so it's equal to 580, and here 800 plus 150. As I told you, every time you will just look at the number because the number might change every time. If there is no difference and it is opened, so directly it's equal to the atmospheric pressure, so it is equal to 740. Don't say 760. Don't assume it is 760, while in fact it's not 760, it is 740 according to the question. And in the other problems, like in the section 5.23, the type of questions is telling me that the volume, the mole of oxygen gas and mole of nitrogen gas are placed in an empty container of volume 20 liters. The total pressure in the container is 0.50. The total number of moles of the gas is equal to what? The mole fraction is equal to what? The partial pressure of oxygen and nitrogen gas is equal to what? And the volume of oxygen gas is equal to fraction of the volume of the container occupied by the oxygen. And we know the rules. The rules tells us that if you want to find the partial pressure of any gas, so the partial pressure of any gas, let's say gas X, which is available with Y and Z, is equal to the number of moles of gas X divided by the number of moles of X plus Y plus Z, which is the total number of moles. And this one, what we call this one? We call this the mole fraction. So we call this the mole fraction. And then if you want to find the partial pressure, multiply this partial pressure by the total pressure of the gas. So here, if you want to find it, just multiply the number of moles divided by the total number of moles, which is the mole fraction, by the total pressure. And if you are asked to find something else, you can find it. So if he give you an example and told you what is the total pressure, I will tell him the total pressure is equal to the partial pressure divided by the mole fraction. What's wrong? I can do that. What if he asked you what is the mole fraction? I will tell him the mole fraction is equal to what? The partial pressure divided by the total pressure. So I can use the equation the same way in 3 ways, because some people think that I can use this one only to find the partial pressure. No, you can use it to find the partial pressure, you can use it to find the total pressure, you can use it to find the mole fraction. Any of the 3 will be okay. What about the fraction of the volume of the container occupied by gas? This is again a tricky question, because any gas inside the container will occupy the whole thing. So it is 100%. Don't forget that this will be 100%. It occupies the whole thing, not occupies a partial part of the gas. All right. So the ideal gas assumptions for the kinetic theory tell me that the gas is made of particles, many particles. These particles move in 2 ways. They are random movement and rapid movement. Why, Mr.? Because they collide with each other, and when they collide with each other, they will also collide with the walls of the container. What happens when they collide with the walls of the container? They will make pressure on the walls of the container, so this is the pressure exerted by it. The average kinetic energy of gas is constant at constant temperature. So if you have gas number 1, and gas number 2, and gas number 3, and the temperature is 24 degrees, what you will say about the kinetic energy? Mr. Some of the students will be tempted to tell me that the kinetic energy will increase as you decrease the mass. As you decrease the mass, Mr. This is totally wrong, because this is not the kinetic energy. This is the speed of movement. This is the speed of the diffusion. So take care, don't confuse the speed of diffusion with the kinetic energy. Why? Because the kinetic energy at constant temperature is what? constant. For even they are different gases, but as long as they are at the same temperature, then the speed of the diffusion will be the same. طيب امال ايه اللي بيتغير؟ What changes when you change the mass? This is not the kinetic energy, this is the speed of the diffusion. The smaller the molar mass, or the smaller the mass, then the gas will be faster diffusion or effusion. Faster diffusion or effusion, yeah, Mr. Why? Because it is easier to move. Mr. What is the difference between diffusion and effusion? Diffusion is when the particles move from an area of high concentration to an area of low concentration. If this diffusion happened also from high to low, but through a very tiny hole or tiny orifice, then I will call this one, instead of fusion, I will call it effusion. The speed also of diffusion and effusion is the same. Both of them, the speed depends on the molar mass or the particle size, okay, the particle mass. So as the temperature increases, the particles move more rapidly. They collide with the wall of the container more frequently and more strongly. Mr. This means that if you increase the temperature, what will happen from 20 into 30? What will happen? The kinetic energy will increase, Mr. But what will be the kinetic energy for the three gases? It will be again, take care, it will be again what? The same again. It will be again the same. Take care, you are speaking about the kinetic energy. If you increase the temperature, the kinetic energy will be more, but it will be the same for all gases. This is what's written here. As the temperature increases, the particles move rapidly, collide with the wall of the container, and more strongly pressure. So as you increase the temperature, the pressure of the gas will also increase. This will actually help us to learn the different laws of the ideal gas. So I can say that ideal gas, for example, I can say that some of the equations of ideal gas, I can say that P1 over, I can say that, let's first try with the equation of the PV equal nRT. So PV is equal to nRT. So Mr. if you have two gases which have the same number of moles or same R, I will say PV over R over NT equal to PV over NT. So this is 1, 1, this is 2, 2. Mr. PV is equal to nRT. This is RT for the first, this is NT for the first gas. So PV over N1 T1. And here is N2 T2. So Mr. if you fixed one of the units only, what do you want to fix here, Mr. If you want to say that the pressure and the number of moles is only changing. So pressure and the number of moles. So you just copy this one, sorry. To copy this one and say, Mr. if there is pressure is changing, the number of moles changing, but volume and temperature is fixed, volume and temperature is fixed, I will say P1 over N1 equal to P2 over N2. Now what happens if you change something else? I will also copy it again and say, Mr. if you are only having pressure and temperature, so if you have only pressure and temperature, you will cancel the volume and cancel the number of moles, cancel the volume and cancel the number of moles, and say that P1 over T1 is equal to P2 over T2. What if you have pressure and volume only? So if you have pressure and volume only, what you will say, Mr. in this case, I will keep the number of moles fixed and the temperature fixed. So I will say P1 V1 is equal to P2 and V2. Mr. what if there is number of moles and volume and temperature and everything changing? Then just write it as it is, P1 over T1, P1 V1 over N1 T1 equal P2 if V2 and N2 T2. Mr. don't forget that in some of the questions we use the mass only also. So if you have, for example, a certain gas and you have mass, you can change, take care, this is very important. You can change the number of moles and put what instead? The mass. Why, Mr.? Because you are speaking about the same gas, right? So if its pressure and volume changed and its temperature has also changed, then you can say also the mass is changing. But what will be the ratio? It's equal to M1 over M2 also. So you can also say remove N1, N2 and put M1, M2. Why, Mr.? Because when you put this one like that, you can say that the number of moles is equal to mass over more mass. You can remove this one and put mass over molar mass, and remove this one and put mass over molar mass. Mr. isn't this the same gas? Yes. So isn't the MR the same? Yes. So we can just cancel this one and put M1 M2, and it will be valid. This is not common, but it comes in the questions, and it will be a little bit confusing if you don't know about it. Okay, so this is if I change the conditions. If I don't change the conditions, I would just say that P1 BV is equal to nRT. And in some manipulations of the questions, I can just remove the n and put mass over molar mass. So the equation will be changed into PV equal MT, or I can say PV MR بتساوي MRT, or I can put the volume down here and say PMR equal to mass over volume RT. And since the mass over volume is equal to density, so I can say that. So I can density is written like that or written like that. So equal to density. I can remove this one or equal to D, and then put the D instead of it. I will say PM is equal to DRT. This is all manipulations of the same equation. And in order to answer these questions correctly, the pressure has to be in which unit? Atmospheric pressure. The volume must be in decimeter cube. Don't always forget to make the volume in decimeter cube. The number of moles has to be in the unit moles. The temperature has to be in Kelvin degrees. Or if the temperature is not in Kelvin and you want to change it into Celsius to Kelvin or Kelvin to Celsius, you have to say that the Kelvin temperature is equal to the degree Celsius. So the temperature in Kelvin is equal to the temperature in Celsius plus 273. And if you want to find the temperature in Celsius, you will just do the temperature in Kelvin minus 273, then you will find. Another point that you want to check after that one is the difference between the real gases and the ideal gases. The difference between the real gases and ideal gases. So since we already spoke about the real gases here, we can just take the information from here and modify it a little bit in the real gases. So we said that there is nothing called a real gas in the real world, because most ideal gas in the real world. In our world, all the gases are actually real gases. So they don't have these properties. They are not tiny masses with they are not tiny or point masses. They have volume. They have volume. Even if this volume is a little bit small, but I can say that they have volume. The second thing is that the particles here said that the collisions of the particles here are elastic. Particles are elastic. You know in physics that when the collision of particles are elastic means that there is no loss of energy. When this car hits this car and there is elastic collision, then there will be no loss of energy, and this does not happen in reality. Actually, in reality, there is change in, because if you hit this car, there is some energy will be lost, and it will come out as big sound, as light. It might cause some fire. So the collision is not elastic like in the ideal gas. So collisions are not elastic. And what does it mean that the collisions are not elastic? That they exert forces. So exert forces on each other. What does it mean, Mr. Mister? Here it says there is no attraction between the particles. So there is no attraction between the particles of the gas, but here there is attraction. There is attraction between the particles and each other. Mr. The most important question in this part, because this does not come in the exam a lot, the most important part is when you tell me that there is nothing called ideal gases. All the gases in life is real. So when is the point that the gases becomes real, and when it becomes ideal? It will never become ideal, but when it becomes a little bit more real than ideal, this happens when the pressure is very high pressure, and when the temperature is low. Because at these 2 points, there is too much attraction. High pressure and low temperature, because this is the points at which there will be much attraction. So the particles, there is attraction, so the particles will be like the real gas. They will ask you in the exam, where is the point when the real gases becomes real? I will tell him that this happens when the pressure is high and the temperature is low. Here. So the last or the second last thing, which is the laws. So I have the Charles law, the Charles law. So this is the Charles law. So the Charles law, it tells me this is the relationship between the volume of the gas. So the volume of the gas and the temperature. We'll say that the volume is directly proportional to the temperature. As you increase the temperature, the volume increases. This is if you have a fixed mass or a fixed number of atoms. What is the shape? The graphs of V versus T and T versus V over T versus T and V versus T will give us a direct relationship. It's a direct relationship because they are directly proportional. So whenever the volume increases, the temperature will increase also. What? Okay, so if I compared the pressure, so if I compared the pressure and the temperature, I will see a curve. We have to draw how to draw the curve, because in this curve the temperature increases and the pressure increases also, causing the temperature increase as long as you are increasing the temperature. And you have to know that the line here, if you extrapolate the line here, it will come at a point which is minus 273. At a point which is minus 273. Boyle's law is the relationship. If you have a pressure of a fixed amount of gas is inversely proportional to its volume. So Boyle's law, I will say the relationship is between the pressure and the volume. So I know the pressure is inversely proportional to the volume. If you increase the volume, the pressure will decrease. If you decrease the volume, the pressure will increase. I think this will be all. The last thing is to mention the relationship between the kinetic energy to the diffusion speed. Mr. You said that the kinetic energy is something and the diffusion is something. Yes, if you have a specific fixed temperature, then the kinetic energy will be fixed. But if you increase the kinetic energy, the speed will increase. According to what? According to the relationship between two gases. So if you have gas number 1 and you have gas number 2, we said that the speed of gas number 1, so the speed of gas number 1 is equal to the radical of the molar mass of the gas number 1 if it is divided by the molar mass of gas number 2, which will be on the speed of gas number 2. So the speed of gas 1 over gas 2 is equal to the molar mass of gas 2 over molar mass of gas 1. And there is, of course, a lot of questions that we need to answer so that we can revise this one. And we can just say that the kinetic energy of gas number 2, kinetic energy of gas number 2 over and kinetic energy of gas number 1 is equal to T1 over T2. So equal to T1 over T2. Okay, so the last thing that we need to do is to answer a lot of questions and then try to see what is the problems that it's a little bit difficult. One more important point, if we collected a gas over water, then the pressure of the gas is equal to pressure of atmosphere minus pressure of water. For example, I'm making an experiment, and in this experiment, I have some gas released, like volume gas or whatever gas is released, and I want to keep this gas with me. I don't want to lose it in the air. So I will collect it over water. What does it mean over water? It means that I will get an inverted cylinder here, and when I start the experiment, I'll put this cylinder in a trough full of water. There is water, and there is water here all the way. Once you start to put the gas, so let's imagine that this is the gas and it's moving and going inside here. Once it goes inside here, in order to go here, it has to push the water down. So it will push the water down a little bit and sit in its place. When the water goes down from here, it will go up from here. So in this case, I will say that the pressure of the gas collected over water, which is this gas, so this gas collected over water is equal to the atmospheric pressure minus the water. So where is the atmospheric pressure? This is the atmospheric pressure outside the mister, and this is the pressure of water. The water here has some pressure here. Why, mister? Because this one there is some water vapor. It's not only the gas. There is some water vapor. So pressure of water and here pressure of gas. Mister, these two are pushing the atmospheric pressure. So the push of the atmospheric pressure is equal to the push of the gas plus the push of the water. So if you want to get the push of the gas alone, you will have to put it alone and then you will get the pressure of the atmosphere minus, with the water in the other side, minus the pressure of the water, which is the same equation that we have given here. We'll also answer some questions on that maybe in the next time. So the next time, Bismillah.